Hi guys, now we are going to discuss a new chapter from chemistry, inorganic chemistry, that is P block elements. It is a very big chapter and also it has a good weightage. P block elements consist of the trend involved in a periodic properties. At the same time, there are various compounds with their structure and the chemical reactions. So, what do you mean by P block elements? The elements in which last electron enters in p orbital are called as p block elements. So, this is the definition. Okay. Now, what is the position of p block elements in a periodic table? In a periodic table, p block elements are placed in group 13 to group 18, and those elements are boron, aluminium, gallium, indium and thallium. So, this is group 13. Carbon, silicon, germanium, tin, lead. Nitrogen, phosphorus, arsenic, antimony, bismuth. Then we have oxygen, sulfur, selenium, tellurium, polonium. Okay. Then the halogens, fluorine, chlorine, bromine, iodine and acetine. Then we have inert gases. Okay. Helium, which is not a p block element, but since it is an inert gas, it is kept in a last group 18. So, neon, argon, krypton, xenon and radon. So, these are the elements which are called as p block element. So, this is 13, 14, 15, 16, 17 and 18. It is also called as a zero group. Okay. So, the general electronic configuration, here the electrons start entering from p orbital. So, p1, p2, p3, p4, p5, p6 this way. So, this is boron family, carbon family, nitrogen family, chalcogens or oxygen family, halogens. Okay. So, we are going to discuss one by one group. We are going to study that one by one, and at the same time we are going to compare among these groups also. But very important thing, we need to understand the periodic properties for each group. Okay. So, first group which we are going to discuss now, that is boron family. group 13 elements or boron family. So in a boron family we have boron, aluminium, gallium, indium and thallium. So atomic number of boron is 5, then 13, then we have 31, 49 and 81. So if I consider the electronic configuration 1s2, 2s2, 2p1, 1s2, 2s2, 2p6, 3s2, 3p1, and if you go on writing so on, so here we have 4s2, 4p1, 5s2, 5p1, 6s2, 6p1. So the general electronic configuration for valence shell. For valence shell of these elements is ns2 and p1. Okay. So now the first periodic property which we have to discuss, that is atomic size. So when we are comparing the atomic sizes of these elements with group 2, okay, if we consider the atomic size of boron with the atomic size of beryllium, it was observed that the size of the boron is smaller than that of the beryllium, and it is obvious as we move across the period, atomic size goes on increasing because effective nuclear charge goes on increasing. So the trend in atomic size is as we move across the period, atomic size goes on decreasing because there is an increase in effective nuclear charge. Therefore, atomic size across the group, across the period, atomic size of group 2 elements is greater than group 13 elements. Okay. So this means beryllium is larger than boron. Similarly, magnesium is larger than aluminium and so on. Now, moving down the group. As we know that as moving down the group, the number of shells goes on increasing. So since number of shells goes on increasing, atomic size also goes on increasing. So general trend observed over here is, so it must be like this way. Boron must be smaller than aluminium, than gallium, than indium, than thallium. But there is some exception. Observe the size of the aluminium and gallium. There is not much variation, or the change in a boron and aluminium, the change in a gallium and indium is not similar change observed in aluminium and gallium. It is because of the introduction of d orbital in gallium. So the general trend, if we consider, this is the general trend. The atomic size of boron is the smallest one and the thallium will be the largest one. So this is about the atomic size. Now I will go for the next periodic property, that is ionization enthalpy. The amount of energy required to remove electron from the valence shell of an isolated gaseous atom is called as ionization enthalpy. Now ionization enthalpy is inversely proportional to atomic size. So it is obvious that the ionization enthalpy of group 13 element is greater than that of the ionization enthalpy of group 2 element. So ionization enthalpy of group 13 elements is greater than that of the group 2 elements. So ionization enthalpy, first ionization enthalpy of boron is greater than that of the beryllium. Similarly, first ionization enthalpy of aluminium is greater than that of the magnesium. It must be like that way only. But that is not the true, because if we consider, so this must be the trend actually, but it is observed that ionization enthalpy of group 2 elements is greater than that of the ionization enthalpy of group 13 elements. Now what is the reason behind it? So let us consider example. If we consider beryllium, its electronic configuration is 4 is the atomic number. So 1s2, 2s2. Now if I consider boron, so the electronic configuration is 1s2, 2s2, 2p1. Now if we observe carefully, in a beryllium, electron is actually present in s orbital, while in a boron, last electron is present in a p orbital. So in all, to remove first electron, we require more energy in beryllium because of greater penetration effect as compared to that of the boron. So I can say this way, in here this electron has a greater penetration effect, and because of the greater penetration effect, here we require more ionization enthalpy, which is unexpected, which is abnormal. Okay, so this thing you have to remember. When I am talking about group 13 elements, ionization potential is greater than group 2 element, is not true. This is a false statement. Now why false? Because of the greater penetration effect observed in case of beryllium, rather in group 2 elements. Now moving down the group, here the general trend observed, atomic size is inversely proportional to ionization enthalpy. So the trend in ionization enthalpy will be boron has highest ionization enthalpy, than aluminium, than gallium, than indium, than thallium. Actually these elements may contains 3 valence electrons, so there are 3 ionization enthalpies. First ionization enthalpy, first electron we have to remove, second and third. So if we consider the total ionization enthalpy trend, so this is the correct trend. Okay, so this is all about the ionization enthalpy and atomic size, the periodic properties. We have to see few more properties that we'll discuss in the next session. Thank you.